So welcome everyone to the design and simulation session. My name is Guillaume Montandon. I will be the moderator of this session with Anthime FARDA. Anthime, do you want to introduce yourself?
Yes, quickly. So I'm Anthime FARDA from CA, and my background is in simulation electronics.
And so myself, Guillaume Montandon, I am from Egis and I'm in charge of the digital engineering department. Today, we will have 5 presentations from all over the world, from UK, Canada, France, and even someone from India. The presentation will last 15 minutes. Then we will have some time for the question. For the question, you should use the Slido functionality within Teams in order to ask your questions and vote for the questions. And then we will ask the question at the end of each presentation to the speaker. The subject of this session is how to improve the performance of our projects through design and simulation, and what are the methods and tools implemented within international nuclear companies. One last thing before to start, the session is recorded and will be available within a few days on YouTube. And at 4 p.m. you will have a tech demo available only on the Sfen index application on your mobile. And now I let the floor to Anthime in order to introduce our first speaker.
Thank you, Guillaume. So our first speaker is Victor Richet from Assystem. Victor is heading digital activities for Assystem Group in India, which includes international digitalization of engineering and valorization of tool and methods portfolio for external clients. He originally has a background in nuclear engineering and has specialized himself in digital and system engineering. And now Victor will be presenting you about advanced process modeling and digital twin definition in support of large international nuclear project. Victor, the virtual floor is yours.
Thank you, Anthime, and good afternoon, everyone. So I am currently sharing my screen. I hope you are able to see it. I will not come back on what has been said. I will be presenting the path we have followed from process modeling to definition of digital twin in order to support one large nuclear project, international one. Well, first of all, obviously, I'm going to present what is that project we are using, why we have implemented such an approach on that project, which path have we followed to do so, what have been the results and the benefit of that approach, what did it brought to us and what will it brought to us, and what will we do next afterwards. The project on which we have implemented that approach is the Jaitapur nuclear power plant project, which has not so far started, which is a large nuclear project of EDF and French technology, EPR technologies, which will be built in India. Let me just underline a few key facts so that you get a good idea of the complexity of such a project. It will be, when completed, the largest nuclear site in the world. Production-wise, it will involve more than 50 buildings and a few millions of engineering hours. To add to those layers of complexity, it will be performed by teams which will be located in both India and France. Of course, it will be fully performed in English and in an Indian context between two main stakeholders, EDF and NPCIL, Nuclear Power Corporation of India Limited, and various other stakeholders which are going to take some elements of that portfolio of building and of complexity. Now, why did we choose to implement such an approach on that project? Well, the first reason is not written on the slide, but it's the most obvious one. Due to all those elements, international context, high numbers of buildings, high duration, high cost, etc., etc., this project is very complex. it's very complex to handle, to monitor, to ensure it is delivered on quality and on time. That is why to do so and to ensure each team and engineer will work in a good environment and will have the ability to perform his work in an organized and coordinated fashion, the tool architecture to ensure document and data storage, document and data accessibility, etc., this digital architecture, this tool architecture must be as much as possible anticipated and tailored as accurately as possible to the need. That is why we have chosen to use modelization from the activities that are to be performed all the way up to the tools that will be used to perform those activities. We have chosen to use modeling to represent those activities and to ensure at each step of that consistency as much as possible, to ensure that there will be no interfaces left behind, no activities outside of tools, no data outside of the global data model, with two goals in mind. Of course, to have the right tool for the right activity, no activity outside of the tool, but no tool which are useless. It's in that area all a matter of dimensioning from the engineering streams and sequence, from the org chart, all the way up to the tools that will be used to support those activities. Now, what were the main issues that we were trying to overcome through that approach? Well, first of all, when I said complex project, what I could have said is various stakeholders with various perimeter. First, mapping those perimeter is a challenge in itself. Mapping the org chart, which is of course always changing the, let's say, role and responsibility landscape, is one key takeaway of that modeling approach. Of course, when we say org chart and role and responsibility, you have to put in front of the roles and in front of the responsibility the relevant technical scope to ensure that all, once again, we are in an exclusive and exhaustive approach. All perimeters are covered and no two entities are covering the same perimeters. Of course, when you say role and responsibility, when you say technical scope, you say interfaces as well, mapping those interfaces in order to ensure that due data are providing on time and on quality for all stakeholders to perform their work is a challenge in itself, and anticipating that is also one key takeaway of that modeling approach. Of course, from all of those, well, that also ensures that all activities are efficiently mapped, defined, and allocated, which is one of the challenges to know who has to do what and when. The next question is the end result. Such exhaustive and holistic modeling approach aim also to represent and share a common understanding of all documentations, deliverables, and data that are to be produced. And last but not least, but I will be back on that on prospective aspect, is it enables to capitalize on that scheme and to reuse it for next complex nuclear project that will undoubtedly come in the future. From the stratosphere, from a very high level, this approach that we have followed can be broken down into three main steps. The first step was the process modeling, which enabled us to identify and share a common knowledge of actors, activities, sequences, and deliverables, to know that all the engineering streams and workloads have been efficiently identified, mapped, and allocated. Of course, and as I was mentioning on the previous slide, the other challenges is to ensure correspondences between the activities, the actors, and the technical scope, which is subsequently the second step of that approach, to represent through models as accurately as possible the product which is to be produced to ensure that those technical scope will be as accurately as possible represented on the model. And last but not least, because it's to some extent the final objective of that approach, is to map from the activities and the product which tools, it can be 3D modeling tools, it can be engineering tools for MEP, for mechanical, for electrical, for piping, which tool will be used to perform which activity, so as, once again, to dimension as accurately as possible those tools. Now, let's zoom in a little bit in what is inside those, let's say, high-level step. Well, first of all, the key takeaway was to define organization roles and interfaces, whereas we are talking about internal stakeholders, the ones that will be part of that journey, or external stakeholders, the one that will be just providing, let's say, regulatory approach or some other element. So coming out with this org chart was the first challenge. Then, through the modeling tools that we have used, we managed to represent on one side the technical perimeters, the systems which are to be produced, the more than 50 buildings that I was mentioning, all the systems which are encapsulated in those buildings, and on the other hand, and simultaneously, all the workflows, meaning all the activities and engineering sequence. The challenge is, of course, to make those three bricks match so as to know, as I was saying, who will perform what activities on what perimeter. And then the last, not the last, but one of the last really modeling elements of that approach was to represent the system and tools, and through the use of dedicated modeling tool to ensure that those tools are mapped with the activities and technical perimeters. That gave us almost automatic generation of the functional specification of the information management software that is to be used for that project, which will use several, let's say, large scope tools about 3D modeling, about PLM, etc., but also a key overview of the interface that are to be foreseen between those large scale tools, PLM, etc., with engineering and authoring tools, pipe stress and all specific tools to perform specific computation. Next step being, of course, to implement that information modeling system in order to be on time for the project. Now, let's be a little bit more down to earth. Those are some overview of the model that have been made. One of the added value of this approach, of course, is not only through those graphical aspects of model to ensure that we can gather all stakeholders to finalize those elements, which I must admit is much more efficient than gathering 10 people around one Excel spreadsheet. Let's just say that. But also all of those elements are made in an interconnected manner that enables navigation from one to the other. So to go from one actor to its technical perimeter, to the activities which are encapsulated in that perimeter, to the tool used to do so, keeping track of, first of all changes, and second of all, of all interfaces which are mandatory to perform those activities, so as to ensure proper impact analysis when a change occurs. And I said when and not if on purpose, because as we all know, of course, for each of those projects, change will occur. Now, once again, let's dive a little bit again in the model. You can see on the right part of your screen the video which is unrolling, which is displaying the model and also the navigation in that model. First of all, we are at the layer of the organization, which are part of that. Of course, what is represented on the screen is only a very, let's say, partial view of the model, obviously. And the idea is really at this first step to map the right resources, to identify them, to allocate them. Thanks, and that is one of the reasons why we chose this tool, is to enable that navigation from the activities, from the resources, and from the entities to the activities which are performed by each resource. Those activities, as you can see,
Victor, 2 more minutes, please.
Those activities, as you can see on that model, are allocated to different tools. The benefits of that from technology provider point of view is to ensure good mapping of the involvement of each stakeholder. For the utility, of course, when all those data are centralized, it enables and it makes the handover at the end of the engineering much more efficient. In addition, we keep track of all the changes, meaning that not only we will have access to the data, but also to its history. For all people involved, it enables to have quickly an overview and an holistic view of changes and evolution. And for the builder, of course, the impact analysis is a key thing, because as I said, changes have been, are, and will be occurring all along the project. Now, the next step is, of course, capitalization. To ensure for coming project of that kind, this kind of model will be a basis and we will not need to reinvent the wheel at each time. It is currently used also for onboarding of people in that project, and it will be later on used as a proof for compliance and verification and validation. That is it from my side. Thank you very much.
Thank you, Victor, for the very comprehensive and for keeping track of time. So just as a reminder to everyone, you can ask your question during the presentation in the Slido application. The link is on the conversation. So please do. I have some questions for you, Victor. First one is from Ben Reynard, which is, have you used any enterprise architecture standard in the modeling efforts?
So maybe some of you have recognized the tool which was behind. The name of the tool is Capella, and there is a subsequent methodology which is Arcadia, which defines which kind of object, which defines the meta models and the underlying method, which is based on SysML in a nutshell. So yes, we do follow that framework.
Okay, good. Another question from Jean-Bernard Thévenant. How many people are required for operating the whole data management system?
So far, given into account the little perimeter that we have taken for that modeling, we have reached a number below 5.
Okay. Thank you. Next question from Claude Duval. I'll give time for Claude to add some extra details on the question. I have what is the actual use of the modeling? That's it.
Of course, first use, as I said, was to dimension accurately the tools that are to be used in terms of number of licenses, in terms of duration of use of those licenses, etc., all of which resulting for the correlation between the activities and the tool. So that was goal and use number one. Second use is, of course, to do impact analysis and change management. So as if there is, let's say, a switch of scope between two entities or a scope evolution, to be able to compute as accurately as possible and as quickly as possible the impact in terms of IMS, dimensioning, information management system dimensioning.
All right. Thank you. Next question from Jean-Bernard Thévenot again. What are the key features which make you choose Capella?
Well, first of all, it was readily available and very easy to deploy. So that was one thing. And also, well, two features were really important. First of all, that is a tool which is covering both organization modeling and system modeling, which was a feature completely necessary if we want to allocate the proper technical perimeter to the proper entities and organization. Of course, it is far from the only one tool doing that, but it was also doing that with encapsulated framework and method. So we don't have to, let's say, go through the definition of data model. So those were the three main elements that made us go to Capella.
All right, thank you. Two questions that are look very similar on the business standard that you used for developing the tool, and there's a mention to data libraries or data dictionaries, ISO TS 15926.4, something like that. Does that ring a bell to you? And did you use such standards?
Nope.
Okay.
Well, so far, to be terribly honest, for organization mapping, except Arcadia, as per the use of objects, we didn't follow any standards. And of course, for mapping of technical perimeter, as we are talking about EPR technology, we follow the EDF coding system, ECS.
All right. Then I will bring a question on my side. Sorry for that. Which is you presented the all your development as an application to the JDataPool project, and the question is, to what extent is that specific to JDataPool, and how could it be applied to other projects, and what kind of adaptation would you need to perform?
Well, let's split the question in two. Of course, this is highly in three. This is highly adherent to the JDataPool project organization, so that component needs to be redone every time. It is as well adherent to EPR technology. So if the intent is to deploy it for other kind of nuclear facilities or other kind of technology, the technical perimeter needs to be rethought as well. But the overall approach and the overall methodology, step-by-step methodology, this is for me completely generic and could be used and reused for any kind of complex project.
Thank you. Okay, so I guess we are out of questions now. Everything has been asked. I thank you again, Victor, for that presentation. Guillaume, I will let you introduce our next speaker.
Thank you, Victor. So our next speaker is Ben Reynard from Atkins in the UK. Ben is a chartered mechanical engineer who joined Atkins SNC-Lavalin in 2012. And Ben leads the development and deployment of technology initiatives for SNC-Lavalin in the nuclear new build sector and sits on cross Atkins UK and Europe digital twin leadership. Ben has recently supported nuclear new build clients including EDF, Sizewell, GE Hitachi, and Rolls-Royce SMR in the development of digital engineering and integrated project delivery environments. His current project portfolio is working to accelerate the realization of benefits from the application of digital twin technologies and applied data science to the delivery, operation, and maintenance of complex engineered assets. Ben, it's your turn.
Thank you very much, Guillaume. And good afternoon from my time zone, certainly. I think there might be some people who might not be quite in the afternoon yet. But so I won't bother introducing myself after Guillaume, but I wanted to start this presentation with a bit of a joke that I have, because every digital twin session that I attend with clients usually ends up with an argument around the definition of digital twins, rather than focusing on the problem statements that we're trying to solve. And I think digital twin as a buzzword has become a little bit of a difficult topic in some environments. I see some clients moving beyond the use of the word digital twin, but I think we should generally be less pedantic as engineers and just move forward. There's a good enough definition here on the screen, and I think the key things for me are, it's a digital representation of a real world entity or system, but that might be a system that is to be rather than as is, and the definition of a digital twin and the development of digital twin is a journey. And I think maybe there'll be a theme around some of the presentations today around being on that journey. So in the UK, we've had a programme around national digital twins for a number of years now, and we've had some central academic and government support in the development of some of our definitions. And one of the key things that have come out of that work stream, and that's the UK National Digital Twin, and things like the Apollo Protocol, which is being developed at the moment, and the Gemini papers, is that ultimately we're trying to use data to make better decisions. And if those better decisions can be beneficial for society, then we should focus on those. And I think in the nuclear sector at the moment, we have a big part to play in decarbonisation and route to net zero. And I think the increasing complexity of energy systems around Europe and the world, the digital twins have a real part to play in helping us make better decisions in that context. So key point is ignore the definitions and let's just try and make the world a better place. So one of my kind of key outcomes from application of digital twins is application of data science and advanced analytics. And most of you should be aware of the recent publications around generative AI and things like ChatGPT. But ahead of this presentation, I just asked an AI what a digital twin for a nuclear reactor was, and it came up with these pretty pictures, which I think are a long way away from engineering practicalities at the moment, perhaps. Though if your job is to create pretty pictures for PowerPoint slides, you might be out of a job already. And I think by building digital twins for these complex assets, it's giving us the opportunity to apply some advanced analytics and data science techniques to the data that we have to support better decisions. So I would recommend that if people haven't used things like DALL-E and any of the OpenAI tools that have been released in the last few months, then you should check them out, because it might change your opinion on how close the disruption from some of these technologies is today. So as I introduced, there's various views around the word digital twin, and I think it's certainly been a bit of a hype cycle over the last 3 or 4 years, with clients asking us to develop digital twins, or working with suppliers and software vendors who've rebranded software platforms that were previously modeling or design and simulation platforms to digital twin solutions. But I'd be very interested from the group to get in the chat, or maybe when you ask questions later, where you think you and your organizations are on the hype cycle. So are you in the innovation trigger stage, or do you think digital twins are the best thing in the world, and you're at that peak of inflated expectation, or are you further along the life cycle phase? Personally, I feel our organization is on the slope to enlightenment, and that's a tough struggle uphill, and it's a journey. And I think that's the key message. Climbing up that slope is something that we're trying to do as an organisation all the time. So I was going to ask this as a poll, but you can just let me know in the chat where you think you are, or when you ask a question, or disagree about the definition of digital twin. That's fine too. So articulated this journey, and internally Atkins developed a framework for defining digital twins several years ago now, I think in 2019. And to be honest, the framework looks a little out of date when we go back to reuse it. But the key point that we take forward and when we refresh our framework will be retained, I think, is this concept of maturity levels. And this obviously looks suspiciously like that slope of enlightenment I showed before. I think too often consultancies like ourselves or software vendors are selling the end of the journey as the benefit and not focusing on the important steps that need to be taken along the way to transform an organization or a project to realize the ultimate benefits that we're trying to achieve. And I think any engineered asset or project is somewhere on this maturity spectrum, and therefore can be considered to be on the journey to delivering a digital twin, whether they realize that or not. We certainly see different elements as relevant in different sectors within the nuclear life cycle, be it decommissioning or the advanced reactors or fusion programs that we're involved in. So I think through developing that framework and engagement with the clients and the can-do technology that we have internally as well, we're seeing digital twins being used across the nuclear life cycle, across the projects that we're involved in, and ultimately, this realizes itself as we're collecting more data, we're processing it, and we're trying to use it to make better decisions. And I think this is becoming increasingly normalized, and I hope that's the view that others in this session have too. And then to bring the focus back to the new build market, which is my specialty, and to the effort that Victor was describing on EPR in Jaipur is very similar to an effort I've undertaken on the Sizewell C project on an EPR program in the UK. So perhaps, Victor, it would be worth us sharing notes at some point in the future. I'm very interested in the approach you've taken. It isn't too dissimilar to the approach that we try to take. But a lot of that approach, as you articulated, was to try and manage the complexity of large-scale nuclear new build programs. EPR as a technology is highly complex. Those projects are very, very difficult to deliver, and we've seen that with the cost and delay overruns that we've seen in all the projects that have been attempted to date, perhaps with the exception of Taishan. And I think it's representative of many engineering projects with large levels of complexity. They're wrestling with skills gaps and legacy ways of working. So, in the new build sector, the delivery market at the moment, I do see generally as being stuck a little bit on the information management gap that I think Victor was trying to solve with his efforts in the modelling space. And we need to focus on that information management gap if we're going to ultimately realise the benefits of digital twins. But in the more kind of blank sheet projects, we're certainly seeing digital twins as being key aspects of the delivery plan from the outset. So the plant you see on the right is the UK SMR programme with Rolls-Royce. The digital twin team has been there working on that project since day one. And is a key component of how we're intending to deliver that program. We're also seeing the same in the fusion segment in the UK with the STEP program, and also with other SMR vendors and AMR vendors as they come to market. So I think through our delivery of digital twins and kind of consultancy around them, we are seeing a defined set of benefits that can be achieved through the delivery of digital twins, and we're getting the data to support some of these claims, and obviously the programs that we're involved in are taking up those benefits and trying to realize them. So, improved safety should be at the forefront of everybody's kind of minds, and certainly in the decommissioning space, we're seeing modelling of radiation fields to support planning for decommissioning as a key use case that is easy to implement and will have a safety benefit. The UK Health and Safety Executive are a big proponent of 4D modelling and time simulation of activities and rehearsal of activities on digital assets in order to improve safety outcomes for workers in the field. And those are things that we're actively deploying. As I mentioned at the start, the Gemini principles and the societal impact, us in the UK, like many countries, are aiming for net zero by 2050, and that the modelling that we're doing around hydrogen systems linked to nuclear capacity is something that's helping us to make better decisions and support the investment cases around delivery of those assets. I touched briefly before on advanced analytics and AI and machine learning. Once you've overcome the information management gap and you're deploying your digital twin technologies, I think this is one of the real benefits that remains perhaps to be sized in terms of opportunity. But we're certainly working towards deploying these types of technologies on assets today. And then, the standard industry literature, and some of this comes from techno-economic assessments from UK SMR programs. Having these technologies through the life cycle of the project should be able to deliver a 10% capital reduction, and then through into the life cycle of the asset should be able to deliver 20% OPEX improvement. And the OPEX improvement from advanced asset management, we are seeing in our highways sectors, in our rail sectors on those programs as real data. So we're actively trying to bring that benefit to our UK nuclear programs. And one of the targets I think that we've got is driving the use case to close the information management gap. But with small modular reactor programs, fundamentally the business case is driven by digital twin technologies. When you move to a smaller reactor with a smaller power output, you lose economies of volume that have been developed over time with the large scale programs, and you have to be much more efficient with the operations and maintenance of the asset to come to cost parity with the large scale programs. So the anticipation is that the small modular reactor programs will run with vastly fewer members of staff on site, so targeting working staff arrangements of around 80 to 100 staff on site, and that's very different from the large scale plants. And to achieve that, they will need decision support tools and better data about the asset that they're trying to manage. Obviously,
two more minutes, Ben.
Yeah, the SMR vendors themselves are, Rolls-Royce and GE have aerospace backgrounds where they have moved to service business models in terms of operating their fleet of aero assets, and they're very much looking to deploy that kind of business case in the small modular reactor market as well. And to do that, you need networked digital assets and management techniques to be able to deliver that as a service. So my view from operating in this space is that the tools and systems are there to be used. The technology is not a limiting factor. We're getting great progress in developing information management standards and common frameworks. There is a skills gap, but if we focus this on data engineering, data science, and visualization skills, those skills are in the market, and we have a developing cadence of projects in the nuclear renaissance with the small modular reactor programs and with the EPR programs, where we're taking the learning from each project as we go and starting to see those benefits aggregate over time. And I guess the key enabler that we need to see in the market is a problem to solve. And I've articulated that SMRs might have a fundamental business case towards moving to digital twin technologies, but the net zero ambitions of Western democracies at the moment is a problem that we need to solve. And I think fundamentally that is an enabler for digital twin technologies. So I think sometimes the grass is always greener when we look around at other sectors and other industries that they've made bigger strides forward with the deployment of digital twins or machine learning or AI. And certainly we've seen big disruption in things like travel and insurance. I'm sure all of you go on price comparison websites, and those are largely driven by AI these days. And I think in infrastructure and asset engineering, it is proving to be a slightly different challenge. It's a slower burn, and I think we're on that slope to enlightenment. And it's just about aggregating the smaller victories. Every time that we move from unstructured data systems to structured data systems, every time we implement and agree information management standards, every time that we move from on-prem systems to cloud-based systems, we're slowly crawling up that slope and making progress. So, I'm off the back end of COVID in the last couple of years, starting to see quite a lot of benefits that are being unlocked on these major programs. So I think it's a good thing that we should recognize between us all that we are making progress. Thank you very much.
Thank you very much. We are a bit over time and we have some questions for you, Ben. So the first question is how to make sure that organizations consider all the linked digital twin components across life cycle and don't just have completely separate IM, I guess, information management and modeling pieces.
Yeah. So I think in the UK, we have a framework for information management called ISO 19650 that we developed, which is now an international standard. Those processes for developing information management capability within organizations and projects always start with the end in mind and have a section called organizational information requirements, which is considering the high-level strategic implementation that's required to meet the organizational objectives. So I think organizations should definitely get their high-level strategies in place before embarking on technology selection or procurement or isolated efforts that don't realize benefit when they can't be integrated together.
Thank you. The next question is, do you see IP, intellectual property, issues related to digital twin used in an extended enterprise framework? Is it required for each data to protect it according to IP? If yes, is it a huge obstacle for digital twin spread in nuclear industry? From Jean-Bernard Thévenon.
It's a good question, and it's one that is active on many of the projects. The National Digital Twin Programme that I referenced earlier in the presentation did a lot of work about something called a data commons. So it's about enabling data use for the public good. So there's data that would be private data and there's data that would be used for the public good. And I think that process can be applied in the project space that we're seeing. So some data will be protected IP, and there are lots of clauses in information protocols that enable that to be protected in a common data environment. But there's also data that is of a common good to all parties. So it reduces the risk of project delays and overspends, and therefore the benefits of getting past that IP problem are probably significant. The nuclear industry will die if we can't deliver on time, on budget, for our investors and stakeholders. So it's in all of our interest to get past that IP blocker.
And one question which is a bit linked to that, do you think lessons are being learned appropriately between different projects with different companies? Is there more that could be done to enable collaboration to solve problems?
I think there's definitely more to be done. And I reference back to that problem I just mentioned, in that if we don't solve, the ability for us to deliver these large scale plants on time and cost, which we're struggling to do, other technologies will take the place of nuclear. So within my organization, because we work across the different clients, we do get that internal share of lessons, and perhaps that's the purpose of consultants in the industry, perhaps to make sure best practice is shared around. But I think as an industry, we need to do better to formalize those shares.
Thank you. The digital twins are keys to help taking the right strategic decisions in complexity. It applies to nuclear. Do you have an idea on the application to climate change issues?
So one use case that we have internally for use of this type of technology, and you can argue whether it's digital twin or not, but it's about carbon accounting through the life cycle. So obviously, carbon is embedded in the manufacturing and transport phases for a lot of assets, and that requires network systems to understand, or communication between suppliers and the asset to understand what the carbon content is. I think that networked systems is a key thing of making better joined up decisions across the life cycle. So that's where I think some of the sustainability challenges can be met. And another example we have is where you're linking hydrogen production to a small modular reactor, for example. When do you use that electricity for power generation, and when do you use it for hydrogen production, and how do you optimize the decision making around that?
And the next question is this data common available?
So if that's referring to the National Digital Twin workstream, there is a paper perhaps that I can share around the data commons concept and how that as an idea might be useful to people in this environment.
All right, thank you. I have one question on my side. I told you I may have some tricky questions. You talked about benefits, and my question is, how did you measure the 10% and 20% of benefits?
Yep. So there is, in the UK, there's been several studies. So for Heathrow Terminal 4, there was an in-depth cost study done on the realization of benefits from the common data environment and the information management practices that were being promoted by government as part of the UK information management mandate. So in the UK, we have a mandate that all projects should follow the UK BIM framework, which is a key enabler, I think, to this area. And there's been several cost studies done by the likes of PwC and other accountancy firms to try and measure the benefits. It's quite an in-depth process to measure benefits and track them through life cycle. So in many spaces now, we're just taking the existing literature that we have and applying that with a heuristic to measure what we think the anticipated benefit is.
All right. Thank you very much, Ben, for your presentation and answering to these questions. We'll move to the next presentation. Anthime, your turn.
Yes, thank you. So it's my pleasure to introduce the next speaker, Timothée Kooyman from NAAREA. Timothée has a PhD in fast reactor engineering, which he obtained in CA Cadarache. He worked at CA on the Astrid program. He was responsible for the development of calculation interface for reactor study. He also developed the CA's Direction of Energy's code for molten salt reactor, and he has been leading an experimental program on the Cabri reactor, and since 2022 is now technical director at NAAREA, who is managing the development of both a prototype molten salt reactor and his digital twin. Timothée, the digital floor is yours.
Your mic is on mute, Timothée.
Thanks. Good afternoon, everyone. I'm going to talk today about something which is a bit more, I would say, technical compared to what was just presented by my colleagues from across the channel. And I'm going to talk about how to link CATIA, so 3D modeling, to a Monte Carlo code for neutronic calculation inside a digital twin, which is a very interesting feature for nuclear reactor design. So just a quick word on what we are working on at NAAREA. We are a French startup who is aiming at building a fleet of molten salt microreactors, so with a power of a few dozens of megawatt electrical. And NAAREA has decided to incorporate the digital twin philosophy at the very early stages of the design in order to leverage everything which could be obtained from this approach. Our plan is separated into 4 phases. The first one is to pre-design the reactor and build a tool around this design effort, to have a tool which suits our needs, and then to go on with a detailed design of the reactor based on this tool. And this should end by 2026, and then start up a prototype reactor by 2030, and then go on with building a reactor fleet. So, as someone said before, everybody has its own idea of what is a digital twin. So our vision of what would be a digital twin, which was worked on with the collaboration of Assystem from France, is based on 3 pillars. The first one is a 3D model of the installation. So we have we work on a common 3D object which everyone can use with tools such as configuration tracking and modification tracking also. So that's the first part. The second part is numerical simulation. So we use simulation tools from the industry, namely the simulation tools which are supplied by the French company Assystem, who works on software such as Abacus, which is well known. And we use their tools for mechanical and CFD calculations. And the last part is data traceability, so which is more about architecture requirements and everything which is linked to tracking that the requirements you specified are correctly met. So everything is done through a Dassault platform which is called 3D Experience. This is the general architecture of our digital twin, and you can see here the black part at the center is everything around 3D modeling and data traceability. And this part here is everything which is already available into the Dassault tools for numerical simulations. So this is mainly CATIA for mechanical simulation, and Simulia, which is built on the Abacus solver for thermomechanics and fluid mechanics simulations. And here you can see that on the right hand side we have some tools which are not available into the standard Dassault suite. This is logical because you don't need a Monte Carlo code to design a car or a plane, but we do need one to make a nuclear reactor. So we had to build interfaces to interface or data hub, I would say, with third-party tools, which are Monte Carlo codes 344 and OpenMC, which are used for nuclear reactor design. So now let's go on and talk a bit about how neutron science do 3D modeling. 3D calculation tools or simulation tools such as CATIA use a volume-based description to represent what is inside, or they use equations to parameterize surfaces, which makes them not quite compatible with Monte Carlo tools which are used in neutronics. On the left-hand side, you've got a cylinder, which for a a CAO tool is a CAD tool is a cylinder. It's a single volume, and on the right hand side, if I want to describe this this cylinder in a Monte Carlo code, I need to say that this cylinder is in fact a region of space which is separate, which is defined as the inner part of the cylinder intersected by well, and everything which is above this plane here and below this plane here. So this is a surface-based description method which is used for historical reasons, and because in a typical PWR assembly, you've got squares and cylinders, and that's it. So there is no need to go into more details. So as you can see, there is no quick and easy way to reconcile these two approaches. So what we've done is that we wanted to build an interface to directly take the 3D model of the reactor, of the core of the reactor, and turn it into a Monte Carlo input file. My own experience at CEA, and I think the experience of most of the people who works in core design, is that usually there is a very high amount of time which is lost in translation between two codes which describe the same object, the same physical object, but their philosophy of description is different, and then you have data loss during this process, and then you have traceability issues because someone made an approximation which he did not correctly trace, and then you lose things on the way, and that's not acceptable for nuclear reactor design process. And there is also a very nice additional benefit of using this approach, is that in a nuclear reactor, differential expansions are very tricky to model using traditional Monte Carlo tools, but are playing a key part in the operation of the reactor and the determination of its feedback coefficients. So that's something which could be done using our approach. And the second point is that we have usually there are approximations which are introduced during electronics modeling, and these approximations lead to biases, which are usually quantified through what is called the calculation scheme, and our goal is to take that into account and design our interface as a complete calculation scheme, starting from a 3D model down to the final strength calculation. You have an example here. This is, I would say, a 2D plane with a 2D piece with a cut corner. Some people would say, that's fine, I will take the time to describe this cut corner, and other people would say, this is not important for electronics, so I would just use a rectangle, and that's fine. So the idea is to have a direct control on the biases we introduce during this this 3D model to Monte Carlo approach. So how did we do that? We use the 3D Dassault platform, and then what we've done is that we built a 3D model for reactor core using CATIA, and then we shifted it to an OpenMC model using a direct translation tool, which I will explain and detail a bit in a few moments. And we also included a materials handling tool. The idea is that when you use iron, I don't know, standard inox for your reactor, the material definition is the same if you use it for electronics or for thermomechanics or for fluid dynamics. So you want to have a unique definition of this material and to save all of its properties inside a single place, which is somewhere in the digital twin, and this should be able to be addressed by every other tools. So we built a material library, I would say, which can feed this electronics model with the information it needs, because what is needed for a Monte Carlo calculation is not really what is needed for a mechanical calculation, for instance. And then what we've done is that we are building the capability to feed back the data from the electronics calculations back to the CFD calculation using import capabilities of the platform. So in a few more details about how we deal with materials handling. So as I said, in CATIA, for instance, materials are stored using their name, and what is stored is the physical parameters, so density, thermal conductivity, or whatever, which can be tabulated in temperature. But for a neutronic calculation, what you need is the atomic density, which are given usually in atoms per cubic centimeter. And this is something which is typically not stored in CATIA. So we had to build a dedicated material library. How did we do that? CATIA has the information of what material is where, and we had to, in fact, see what material is where, what is the temperature of this material in the relevant part, and then carry out some interpolation to get the tabulated densities which are stored by CATIA, and then get the info from another part of the twin which stores the atomic compositions to build materials for the neutronics calculation using the adequate temperature and what is stored inside the digital twin. This way we can have a full OpenMC input file which can be used for criticality calculations and reactor design. So the approach for this algorithm, I would say, is a brute force one. What we did is that using CATIA capabilities, we just meshed our reactor with fifth-order meshes. And we built a converter with some tricks to limit the number of cells and surfaces used inside the input file. And this can directly be used as an OpenMC input. And we can also specify some tallies, so we can count fissions or capture or whatever inside this mesh, which it's quite efficient because we use the same mesh for CFD or mechanical calculation and neutronic calculation. So there is some, it limits the needs for quite expensive interpolation tools. And then we do some reconstruction of the tallies on the input mesh, and we can go back and typically re-import 3D power profile inside CATIA to compute some thermomechanics, for instance. So this is very effective because it can be incorporated into a calculation chain for, I would say, on-the-fly use, because you don't need to be a nuclear engineer to use this tool. You need to be able to manipulate CATIA, but you don't need to know OpenMC, which is always interesting to do some, I would say, quick and dirty work. This algorithm, however, has a few limitations. Meshing curves with a ferrihydron is something which leads to a small bias, because this is an example. You have a piece of circle here. If you use only one triangle to map it, to mesh it, you lose a big part of it. So you need to decide how many triangles you want to use to mesh this circle arc to make sure that you are not introducing more errors in your calculations. So we are introducing, I would say, careful control of the meshing we consider, but this is, I would say, what goes behind the calculation scheme which has to be built. And if we have a high number of meshes, but this is more or less not a problem for us because our reactor is small, this can take a few hours to generate the input file, which can then be reused quite easily. So what are we going to do next? We are working on, I would say, an hybrid export. So we are trying to remove the biases coming from meshing with ferrihydron by building what is called hybrid export. So we replace the cycles or the circular surfaces by surfaces which are defined using the Monte Carlo tool directly. So this removes some biases. We want to also use the meshing capabilities of CATIA, which are quite expensive and quite complete, to automatically change the export mesh depending on the refinement we're looking for in terms of neutronic calculation, and to limit the time required to generate the output file. And a second part with this is also to use varying precision meshing to adjust I would say, the precision of the meshing depending on what we want to do. And so the next step, which is going to start in January, is to then complete the loop and show that we are able to import the output of the Monte Carlo calculation back inside the 3DX platform and use Abacus to make some coupled neutronics and CFD calculation. Finally, as we are going to use that to carry out core design and reactor design calculations, these developments are going to be validated in accordance with the ISN, the French Safety Authority Guide number 28, which specifies how a nuclear tool which is used for the safety demonstration should be used and qualified. So we are currently in the process of testing this interface with our core geometry, which is quite complex and would take us something like a month to do by hand. And now it's only a few hours of tweaking, and then we can directly make some changes inside the 3D modeling tool, and then get the effect on the criticality parameters in a few hours instead of a few weeks. So that's definitely an improvement. And we will also use that for to carry out expansion computations, so which is always a tricky part. And we will integrate this into a full tool by June 2023. And that's it for me.
All right, thank you very much, Timothée, for the very comprehensive presentation. Once again, we have a few questions from the audience. First one is from Jean-Bernard Thévenon. He said, correct me if I'm wrong, due to Monte Carlo convergence time, I guess your computation coupled with thermal hydraulics runs in steady states only. If not, how do you manage thermohydraulic feedback on neutronics in fast transients?
Actually, there are some quite elegant calculation routes which have been developed in the past years, which use transient fission matrices to address this issue. So we are running fast transient using, I would say, I can share with you some papers on the topic, but the idea is that you build matrices which are similar to green function of your reactor behavior, and then you run the CFD, the thermohydraulics calculation, and compute the neutronic state based on these matrices, and this can be done. This is a transient computation done with static tools for the neutronics part. Okay, thank you. You have an anonymous thank you with a question regarding intellectual property, and the idea is that OpenMC uses neutron data that are free for universities and states, but not for commercial company. Do you have an agreement with the owners? So OpenMC is an open source code which is under an MIT license, so its use is it can be used readily by our company, and the nuclear data libraries are freely available, and the data can be accessed by anyone. So I don't believe there is any issues of intellectual property regarding the use of this code. All right, thank you. We have less question on your presentation. I will pick some of mine. Sorry for that. Yeah, first one is you have showed us your 4-phase plan for development, and first step is the development of the pre-design of the reactor and the development of the digital twin. And my question is there links between the two activities, and how do they benefit from each other? Yes, so there are links. Typically, this is the first time, as far as I know, that people from the nuclear industry are using tools from the automotive industry or the aerospace industry. So we discover the tools, and we see what we can do and how we will build the twin based on that. So that's the first part. And the second part is that we are currently, in fact, pushing the design of the reactor to very, I would say, a fine extent, and we need to use this tool because otherwise we are going to spend a very long time making the input file. So we are currently using it now for the pre-design phase.
Thank you. Also, one question that you may have addressed a little bit, but it's regarding the performance of your calculations. You actually explained that the Monte Carlo geometry are very different, well, at least are different from the CAG1, these usual ones. And did you measure, or do you plan to measure the difference in the performance of your Monte Carlo calculation between the creation of a native geometry as compared to the CAG converter?
Yes, we are planning. We are going to run, I would say, a comprehensive series of tests. We checked that the results were the same for basic geometries, and now we're going to run some more detailed, I would say, benchmarking of the performances to see what we're going to lose if we lose anything. Okay, and what are your expectations? I don't know. Given the size and I would say the refinement level we are currently at, I don't expect that much of a performance loss. Good, thank you. Okay, I'll end with one last question on my side. Does the approach you propose impose some specific way to create the CATIA file, or are you able to use the tool with any CATIA CAG geometry that we? And that's a very interesting question, which my mechanical engineers just asked me this morning. In fact, I am nuts. But so there are some rules. We are discovering that there are some rules which should be followed in the mechanical design part to make sure that the piece can be translated into a mesh by CATIA. But that's some internal, I would say, issues in CATIA. As long as you are able to generate a mesh of your part, it's fine. Okay. We have one more question on the by the audience. Do you see interest in using standards to exchange data between the CAD model and the calculation codes? The main issue behind the development of this interface is that there are currently no standards which are stable for this exchange. Okay. You can see that in I would say, there are various tools which are available based on MCNP or 344 or OpenMC, which are using third-party software to convert, for instance, a step file to Monte Carlo calculation. But these tools are not suitable for our purpose, mainly due to, in fact, intellectual properties issue regarding the access to electronic codes. So that's why we went into this direction. Okay. Thank you very much. I guess we have no more questions for you. So we'll move on to the next speaker. Thank you. Thank you, Timothée. Our next speaker is Jérémy Bourdon from Assystem. Jérémy has a diploma in complex system engineering and a PhD in MBSc, model-based system engineering, critical infrastructure. He is currently MBSc technical lead at Assystem EOS, who is involved in exploring, formalizing, and deploying system engineering methods and tools on critical infrastructure projects. And Jérémy has a presentation titled Develop and Tool a Model-Based Approach for the Early Study of Radioactive Waste Management Scenario. Jérémy, the floor is yours.
Yep. I'm sharing my screen. Okay. Can you hear me? Hear me? Yes? Yes. Okay, nice. Hello everyone. So today I will talk about how we develop and tool a model-based approach for the early study of radioactive waste management. This presentation will be split in 4 parts: introduction, briefly some characteristics of radioactive nuclear waste infrastructure, the objectives that the method have to meet. I will present after the model-based approach overview and after some conclusion and perspective. First of all, radioactive waste management projects have some characteristics that we have to take into account. The stakeholders' needs and requirements are very numerous, a lot of needs and requirements, and they change during the project and evolve. This kind of project generate a huge volume of data that have to be handled. Also, many alternative solutions have to be evaluated during the project and generated during the project. So this kind of characteristic. And emotioning input data are changing during the project. It's so hard to free some data for the design after, and this has impact on the design after. And finally, a lot of people and disciplines are implied during this kind of project. People that have to communicate between them. These characteristics have some problems with it. It's hard with this kind of project. Data are in a lot of documents scattered in different tools. Scenario description for the management of waste are also in different documents that is hard to manipulate. As I said before, numerous change impact the validity of a scenario. A design can be true at one moment and 2 months after. If this change also.
All right,
I'm back.
Jérémy, I believe we have lost you for a minute.
Yeah.
Sorry for that.
When it have been cut?
Just a few, well, 1 minute ago. So.
Okay. Data are scattered, numerous change during the conception, the design, sorry, and a larger number of disciplines are impacted each other. For example, electricity will have an impact on mechanical fields. So for all these problems, we decide to develop a method with a purpose. The purpose is to gain confidence, efficiency, and reduce project delivery costs for the radioactive waste management project. To achieve this purpose, we defined some objectives that the method have to meet. The first objective is to have a better control of inter-business impact for the technical coordinator on the project. Another objective is to improve the communication support between stakeholders and avoid ambiguities for the communication. Another one is to quickly identify conflicts between different specifications. When you have some stakeholder needs, sometimes, often, you have specifications that are incompatible and you have to manage it. And another objective is to assist the business specifier during the studies. You will see, thanks to the modeling approach, all data displayed easily for the specifier. And finally, identify, analyze, and mitigate the impact of a change in input data on studies is the main objectives. So a model-based approach to support studies, we define this kind of method with three main components: models that will describe which language we will use, which objectives and which concerns are addressed by these models. To support this model, we have to define an approach that will define all the activities that we have to perform, all people to involve, and data that are exchanged between these activities. And also, we have to develop a tool, one tool or another environment of tools to support this approach and this model and implement it to facilitate the handle of these different things. So the approach for this this kind of model-based approach, we defined three main steps for this approach. The first one, we have to describe the scenario and the property of interest with a classical MBSC approach, let's say. After, we will, thanks to data contained in the model, we will simulate the impact of a change on the architecture. And after, a report will be generated and analyzed, and we can iterate for each changement that you have to analyze. So for the first steps, the describing one, we defined three main language to use for the modeling of the scenario. The first one is the physical functional models that will make us able to describe the functional parts and architecture of our infrastructure. And we combine this functional architecture with a physical one, and we can, with kind of description, we are able to see which function are performed where in an infrastructure. We can describe also all the flow in the infrastructure and so on. So it's a statistical description of our solution. The second language kind of models that we use is the influence model, also called structured matrix model. This kind of models connect every property that we want to describe between them, and we describe also formula between this property to describe the influence of a property on another one. To describe further a property, we can associate the kind of measure that the property have, the current measure of this property in one architecture, and also the required measurement of this property to be able to compare the required side with the actual design. And this property can be populated with the same number of measures that you have of alternatives. And for formula models, we just associate different parameters in input with parameters in output with some how to say, function in Python, for example, or things like that. The third kind of model is the warnings and mitigation measured model. This kind of model enables us to connect some rules that we associate with property. For example, one rule that is important is when the property is higher than the required property, we have a warning. And we can also define some rules. When the condition is met, we have a warnings that alert us that a specific domain will be impacted, and with some return of experience that we can put in the model, we can suggest some fix, some mitigation for this kind of problem. For the part of simulation, after describing all the scenario and all the property model, we just have to change the new input data in the property model, and after with with the second model, we can calculate impacted properties using different formulas that we define in the formula model. And for each activities of modelization, it's necessary to have some activity of verification and validation to be sure that the model is correct. And after, we can generate the simulation report and propose some solution, as I said, based on the different conditions.
Just 2 more minutes, please.
Okay. So with this kind of model, we can populate a model with some properties. For example, in this case, we have one model with activity properties, radiological properties, and we change the architecture, and we have been able to see the impact on this property. To conclude this approach, we have developed data model adapted to the study of waste management scenario with the different concepts and kind of models that I present. We implement and federate the different language represented in one model, and this kind of model are also tooled in implement in a tool and extend the tool Capella, for example. And thanks to these 3 things, we have been able to experiment a 40% time saving on the treatment of change impacting the containment class property. It was only on these properties that we made the experiment. Some perspective in short term, it's to extend and generalize our approach for all properties. At the moment, only 1 properties have been treated, the containment classes. We have to perform some tests in real condition with project manager and engineers. The approach has been tested on part side on the project that was already done, and finalize the tool to implement all language that we defined, and integrate this tool with all kind of tools that we could use in our engineering activities. And for mid-term and long-term perspective, it will be to use this approach to instantiate, populate the true digital twin with the different data that we generate with this approach, and build a radioactive waste management digital twin. Thank you.
Thank you very much. So you may have been very clear, because I don't see any question on the chat. So I will sadly start by my questions, and give some time to the audience to add some more for you. So one question is, can you elaborate on the tools that you are using, and what tool do you plan to interoperate it with?
The tool that we used is Capella for the part of functional and physical architecture. And after we extend this tool with development environment that Capella provide to extend with our own data for manage different description of property, description of warning, and so on.
All right. One question from Reynard. What are the integration with other systems you see as important with the MBSE models?
I'm not sure to understand the question.
What do you consider important for integration with the MBSE models?
What is important? For me, everything is important to include in models, but if we have to choose some specific things, at the moment, we just describe the operation of the infrastructure. We don't consider yet other life cycle phases like dismantling or commissioning or things like that. So it could be something nice to include also in our MBSE models. Sure.
Okay. Another question from the audience. Could you explain what do you mean when you speak about containment class property? What is the regulatory framework for that?
I will try because I am not a safety expert. Containment class defines some rules that and design rules to respect, considering the activity of your room, as I know, and it's dependent of the total activity on the room that you analyze. And for the regulatory framework, I don't know the name, but I know that it's a standards that exists and that we use.
Okay, thank you very much. So thank you. Just to stay on time, I will then let Guillaume introduce our last speaker.
Yes, so our last speaker is Patrick Desbiens from Bruce Power. Patrick graduated from Ontario Tech University with a bachelor in nuclear engineering. He started in INC design at Bruce Power in 2011 and worked as a responsible design engineer and owner's engineer for systems such as radiation monitoring, neutron detection and processing, and analog to digital control system upgrades. He moved to the section manager role of the INC Electrical and Computer Design Projects section within design engineering, focusing on delivering high complexity projects in support of upgrading legacy analog control system to more modern digital systems. And in 2021, he joined Bruce Power Digital Transformation Projects and took the lead in 2022. Patrick, the floor is yours.
Introduction, Guillaume. Can you hear me okay?
Yeah, very good.
Okay. All right, good morning, everyone from Ontario, Canada. It's ice pellets and freezing rain outside. School buses are canceled, so here we are. So today I'm just going to talk about Bruce Power and really the opportunity ahead and why we're going towards deploying more modern digital tools, really to set the framework of a digital twin for us, and then how we plan on doing it. So Bruce Power, we have North America's largest nuclear generating facility, about 6,500 megawatts, and that's from 8 CANDU units. We have a 10-year license currently with the CNSC, and we are Canada's largest public-private partner. Some of the other things that Bruce Power is embarking on and has successfully kind of deployed, and one of the items I'll just focus on this slide is producing life-saving medical isotopes. So this is a bit of a an opportunity that Bruce Power is seizing in terms of using the infrastructure we have to produce medical isotopes. We've been doing cobalt-60 and specific activity cobalt-60 for some time now, and we just deployed a lutetium-177 production unit. That lutetium-177 is for fighting prostate cancer. Oh, sorry. So just a bit of background on Ontario's energy supply mix. So the percentages, this is data from 2021. As you can see, nuclear has the highest there, 58%. So again, Bruce Power provides about 50% of that. Then hydro, gas, wind, solar, and just a bit of biofuel. But really, this just kind of shows the grid mix in Ontario, and really the focus on really nuclear here. So what's happening with Bruce Power currently? So we're in the midst of life extension and really extending the life of our units to 2064. So these units were built in 1970s, 1980s. And we're in the midst of doing several things to them. So if you look here at units 1 and 2, they have already had life extension around 2010, 2012. So these units are good to run until about 2040, 2045. Now we're looking at the rest of the units. So how we're doing that is optimization of inspection and maintenance. So we go into maintenance outages now. It's a lot to do with extending the life of the existing core. That combined with asset management, which is basically capital projects to replace our legacy systems and components that are at their end of life. And that's really to gear us up to get to our major component replacements. And really that's just focusing on the 3 major limiting components, which are the fuel channels, the feeders, and the steam generators. So those are your core parts that you can't really access or replace easily during normal maintenance outages. By extending those, really you're extending the life of your units. And then really it's to operate those units safely until 2064. So a lot of opportunity ahead. This is all based on investors' money. And will ultimately directly impact the cost of electricity in Ontario, which gets pushed onto the ratepayer. So what Bruce Power is looking to do is how can I deliver these projects more efficiently to reduce their costs, schedule, and overspends. So just a bit of context on the problem right now in terms of how we do engineering and find information at Bruce Power. So current state, we'd really, let's say whatever project you're doing, this case, we're just going to replace a component. The data retrieval process, I have to go through a lot of siloed systems, through my paper drawings, my specs, my BOMs. I have operational data in several systems. I do have some software for my wiring. And that software is very old, from the 1970s, pretty much looks like a DOS system. From there, in terms of parts replacements, there's a pretty rigorous process behind it in another system. I then start preparing my change, which is really a manual effort of marking up drawings. And between this whole process, you can get a lot of churn. And that churn results in time, in cost, and sometimes rework. Then that moves into the planning and implementation of those projects in P6, which is another division that goes and deploys projects. So what do we plan on doing with this project, which we're calling digital engineering at Bruce Power? And really our vision is to move towards a more data-centric organization and to really have those integrated tools and processes across engineering, our projects, our supply chain, and then on to operations. And the key benefits that we're looking to get out of that is reducing project lifecycle costs and schedule, improving the handover process, and then that kind of longer term improving asset management and monitoring. Anticipated cost reductions, so we'll talk a little bit about the business case. This is ultimately where we can get once we have everything deployed and we're a mature organization when using these tools. So in terms of the business case, so again, touching on why is it that we're going after that? What did we put in our business case in terms of the opportunities that we see with using these types of tools? Really, it's about optimization and the asset management. So perform more work with the same amount of dollars and time. So that will ultimately improve our equipment reliability and prevent portfolio cost overruns. As you can imagine, with this many projects happening, and the fact that we need to continually decrease cost through delivering these projects, that's a main one. Major component replacement. So again, a big one here would be the project handover tools to assist with reduction of return to service, and really the engineering replication effort. That is a very tedious process right now. Replication for us is still a lot of manual effort. And then operations impact on outages. So again, improved safety. There are some tools we plan on deploying to assist our operators and really getting them the information they need on their systems to help them with plant status control, which really gives them a better line of sight to the core. And then opportunities, obviously, for outage performance and whatnot. Again, we're going to be deploying kind of a foundation piece for these tools, which can be leveraged by other organizations. And then a data-driven innovation opportunities. So once we have our information in data format in a common tool set, that should unlock other opportunities for Bruce Power. So a bit on our roadmap. So we are deploying this project in 4 phases. Each phase is really broken up by the tool it's delivering and kind of the capability it's going to unlock. Phase 1 is a handover tool. It's with Go Technology. It's a Hub 2 tool. That is really going to digitize our workflows and processes for project implementation. The key ones here, though, that this project's delivering is the Aviva tool sets. So that is the solution partner we've partnered with, is Aviva. So we are deploying their Asset Information Manager tool, Aviva AIM, which has the Information Standards Manager associated with it. The Unified Engineering tools, which will include Aviva Engineering, Aviva P&ID, E3D, Point Cloud Manager, and the electrical instrumentation modules. And then the last phase is the Enterprise Resource Manager, which is going to support with our catalog management and look to unlock some opportunities with advanced work packaging. So just moving into some of the where we're at today and some of these key deliverables that we've worked through and are working through that I thought was important to share here. One of those is our enterprise class library. So this is setting that data model for our enterprise as we move more towards that asset-centric model. So the way we approached this was starting with CFOS. So starting with version 1.5, which again is an oil and gas standard. We know the Aviva tool works, pretty much already has CFOS built into it under their Information Standards Manager tool. So we started with that at the core. One of the reasons being is that we wanted to adopt industry standard with this. Nuclear doesn't currently have a version of CFOS or anything like that. So that was our base layer. Then from there, we built out what we would consider our nuclear standard or our nuclear data model. So at the end, it really is a combination of the two. You have your CFOS IDs in there, and then where we added those nuclear specific ones, those ones would be stuff like your seismic qualification, your environmental qualification, other types of attributes that wouldn't typically be in an oil and gas standard. And again, Bruce Power, in terms of our equipment classes, in terms of our document classes, we had those built already. So it's just a matter of incorporating the two. A big piece of this as well, in terms of being a brownfield, deploying these tools, is the data transition. So this is a big stream that we're focused on currently, is essentially how do I get from all my existing sources of data, which are siloed in different applications, very paper-based, into these tools so that our projects can leverage that information to then do their modifications within that and get the savings we're expecting in our business case. So currently, just an idea of the extent of the data we have currently. So we're looking at about 800,000 control docs, which would be all our drawings, BOMs, specs. That's under about 22 document types. So yeah, 80% of that is drawings. Our enterprise management system has about 710,000 active location tags. So those are equipment tags. Associated with each of those is about 235 fields, which you consider as your attributes. A lot of these are non-engineering, but do include those engineering attributes as well. In terms of our wiring system, so we have a legacy wiring system that is fairly extensive. So if you look at the content within that, you're looking at approximately well over 1 million new tags potentially if you consider cables, conductors, cable trays, and other structures within that. So the question becomes, how are we going to approach this? How are we going to go after using these new tools while also still leveraging our legacy data and understanding the importance of configuration management at a nuclear facility, which that configuration management currently lives in all our documentation. So that comes under our data transition strategy. So again, we've been leveraging kind of experienced consultants and other vendors, done extensive benchmarking around this topic. We're currently in the midst of deploying a pilot with the Aviva tools. We're moving a project within these tools, and those tools are the Aviva Unified Engineering, and basically to see how these tools, what does it look like when I move my data into these tools? What's that process look like? How do I use the data once it's in those tools? And again, what's the impact on our existing processes and whatnot? So that's that pilot environment we do plan to move within our production. And in parallel to that, we are trying to understand what the market capability is, which we've done within some benchmarking. Again, we are very, very open and willing to try new technologies, new tools to get, for instance, where our data is currently into where it needs to be. So we have a RFI, which will turn into an RFP for this. We're doing some internal experiments to determine legacy tool to the Aviva electrical instrumentation transition. In terms of laser scanning, that is a bit of another kind of segregated process right now at Bruce Power, where we have specific projects doing laser scans. We do obviously plan on leveraging the scans that have been done, but then putting more governance in place and standardization around laser scanning, which we do plan on using for engineering purposes, either to convert to CAD or really to kick off what our 3D models will start as.
2 more minutes, Patrick.
Okay, thanks, Guillaume. And yeah, so data transition for the pilot project was chosen. And then all those learnings are going to get documented into an execution plan in terms of the what, the how, the who, and the when. So this is a high-level comprehensive roadmap. We are really one of the constraints you'll see in terms of the adoption period starting in 2025. Again, we have a business need to get these tools in place by then, so that we can have projects leveraging them and getting savings by then. One of those reasons, if you go back to that life extension slide, is that we have a lot of active work ongoing currently. So we may be missing opportunities in terms of potential replication and other opportunities that we have there, that we want to get in front of that and ensure that we're deploying these tools in time for use from our project teams. So I guess I could stop there, Guillaume, if that's
all right. Very good. Thank you very much for this presentation. We do have some questions for you. The first one from Christophe Mouton. Do you intend to move nuclear site force extension into 15926 ISO? There is currently a project development about a nuclear digital ecosystem framework at the ISO 184 standardization committee dedicated to industrial data. Canada is not represented in the development team yet. I think it's kind of an invitation.
Yeah, okay. Yeah, so in terms of the standards when you look at, again, we are using CFOS for enterprise class library. in terms of data transition and moving to these tools. So we do have a quality management plan that we have. In that, we do reference, I think you said ISO 15926.
Yeah.
Yeah. So we do plan on leveraging that, adopting it fully. I don't think so, but the other side is too that I know that EPRI is doing some work on this, and as well as our CSA standards committee. I know they are currently looking at all this technology innovation that utilities in Canada are going after, and what gaps exist in our current standards infrastructure. So that work's ongoing, but that does sound. I don't know if we can connect afterwards in terms of getting more information on that.
All right. Two questions from Ben Reynard. What are you doing to make sure you have the right skills in the organization to deliver this transformation?
Yeah, that's a great question, because this is going to be, as we understand, one of the biggest risks. I touched on one of them, which is data transition, or challenges, I should say. The other one's going to be change management, because of the I would say that it's going to be a significant shift in how we do work, new tools and whatnot. So we do plan on, obviously, throughout this process is getting those individuals identified. Let's say if they're going to be the admins, or depending what role they're going to do, as soon as possible, so they can support us throughout this transition period here, throughout the implementation. And we do also plan on leveraging contractors, consultants to supplement that skill set early, essentially, to work alongside our engineers until we become a little bit more mature.
All right. The second question from Ben is: are you deploying to cloud or on-premise systems?
Good question. So I would say a combination, and we're working closely with Aviva on that, and working with their product roadmap to make sure it aligns with our project roadmap. Right now, we do have plans to transition our Aviva AIM system to their AIM Advanced, which is a cloud offering. And then for the engineering tools, those will be mostly on-prem initially, and working closely with Aviva in terms of their readiness and roadmap for moving to cloud. So I guess at a high level, Bruce Power does intend to move to cloud where it makes sense. And obviously, we're going to start having a lot of engineering data in these tools, and there'll likely have to be some discussions with our regulator, etc. So that will be part of our roadmap. But right now, it's essentially what the tools have, their readiness ultimately.
Okay. One question from Jean-Bernard Thévenon. Did you make a study between data aggregator, your Aviva AIM, versus a big PLM?
So I wouldn't say we did anything like any extensive studies to that front. We did do, quite a bit of OPEX and benchmarking, like we said, and then we ultimately went for competitive RFP, right? So we did get bids from a lot of the big players on this. What we liked, again, about Aviva was kind of the comprehensive tool sets that they had. Again, we were looking for that kind of common framework, common tool set where the information can integrate well together. So that's ultimately why we went that route.
Okay. There are two questions about identification of tags. Do you use ISO 81346, and do you apply a standard for identification of the object?
So in terms of tag identification, so we really just that'll likely be a process we update. We currently have internal governance that we've had really since Ontario Hydro built these facilities in terms of our tagging standards. So that's essentially where we are currently. That will change though, because basically how we treat an equipment tag now will remain the same, but there will be a lot of new tags that will kind of change that definition. Currently, just based on, if you look at our legacy wiring system, we have our cables, our wires, our cable tray. Those live in that system, but they're not really equipment tags anywhere else. So those will have to be ingested as equipment tags, as an example. Same with our line lists for our flow diagrams, P&IDs. So I would say that our tagging standard processes will expand.
All right. One last question. What is the role of data models and models in general in a so-called data-centric approach?
Yeah, so that's really about data quality and data consistency. So we're working closely, we have an organization internally too, we have a new data governance process. We've done enterprise system upgrades in the past where if your legacy data is free format or if it doesn't have good rules around it, it makes those processes very challenging. So when we look at where we want to be is have ultimately also that term single source of truth, right? So if I'm following that same data standard and data model in whatever kind of application I'm using, you can get that data consistency at your facility. I guess that would be my answer to that at high level.
All right. Thank you very much. I think we are at the end of our design and simulation session. Anthime, do you have any conclusion for us?
No conclusion. I just want to thank all of the participants for their presentation and for everyone's participation. Guillaume, yeah, last word is for you. Then.
All right. Thank you to everyone. Maybe just a reminder, there is a tech demo session at 4 p.m. French time, which will be available only on the app on your mobile. And the next session, what we call the case study, will be on January 5th at 1 p.m. French time. So thanks again to all the speakers and participants for your questions and your interest, and see you soon for the next session and the tech demo this afternoon. Thanks again. Bye.